Can you hear me now? Michael? Are you there? Okay, maybe. Thanks. All right, so let's continue from what we discussed last Tuesday. So we started time-dependent problem, and we look at the first order derivative. So first order derivative comes in heat transfer and fluid mechanics. Okay, and heat transfer dot indicate the heat flux rate, and then fluid mechanics. The reason we have a first order derivative is going to be the primary variable is going to be velocity. So first order derivative is going to be acceleration. So that gives you inertial force. But in solid mechanics, the basic variable is going to be displacement. So inertial force, which include that mass and acceleration, the acceleration is going to be second derivative. That's why you see second derivative in here. Okay, so that's the inertial force. So without inertial force, it's going to be simply static problem. And the method weight residual is exactly the same. You are going to conduct that over the spatial domain, not time domains, just spatial domain. So everything same, the way we do as in the previous chapter, except this term. So this term is we discussed last Tuesday that U is HI times UI, summation of shape function multiplied by the nodal value. But the double dot, the temporal derivative is carried by the nodal variable in here. So UI, nodal displacement, double dot means acceleration. So in other words, plugging into this formula is always looks like that. So this form is same whether this is going to be, we have a first order temporal derivative or second order temporal derivative, doesn't matter. This is all the same form of that H transpose times H, something like that, always this format. And then we have a linear mass density in here. And then if you plug into the shape function we developed in chapter 8, we have this shape function. So this is 4 by 4 because each element has 4 degrees of freedom. And I told you that this mass matrix conserved in terms of linear mass. Linear mass is involved only those 4 terms. The rest of them are not pure linear mass, some kind of rotational mass and then some coupling of that. And as you can see here, A becomes smaller, element size becomes smaller, all of their contribution becomes negligible, either other than those the linear mass. So the basic equation here is, just this the linear mass. Okay, the governing equation. But when you translate into this, Galerkin's formulation like this one, using the same procedure, we came up with this matrix, and this matrix we call consistent mass matrix. Okay, consistent mass matrix. Why we call consistent means that the mass matrix is constructed in the same way as the stiffness matrix. No difference. We just follow same procedure, same shape function. And then we construct the mass matrix, so we call consistent mass matrix. And important thing is always conservation of mass. If you do not have conservation of mass in mass matrix, your solution is not going to be accurate, and also solution is not going to converge it to the right solution as you refine the mesh in your solution. Okay. So anyhow, this is the one kind of mass matrix, and a simple mass matrix here is because, as I said, only linear mass is important, like a V1 and V2. This theta 1 and theta 2, rotational mass is not important in as shown in the governing equation. So that one simple way that if this is going to be uniform. Okay, the geometry is uniform cross section throughout the length of the element. Then simply using lumped mass matrix, the total mass GAL is going to be total mass, which is equal to M, mass of the element, and divide by 2 goes the first node. So again, V1, theta 1, V2, theta 2, and V1, theta 1, V2, theta 2. So only this one, V1 and V2, have this value. The rest of them is going to be simply 0. Okay, and this is called the lumped mass matrix. So we simplify that half goes here, half goes here, assuming this is going to be uniform beam element. Okay, then so this is from intuition, not from any mathematics, just common sense that half goes here. Then obviously some difficulty you may see is that if you're going to inverse this matrix, if you're going to do multiplication, subtraction, doesn't matter. Excuse me. But if you're going to invert, then you have a 0 in the diagonal. Right? Yes.
Well, what was the purpose of this matrix again? You said that it goes like a uniform.
So this is to simplify without going through this derivation. Okay. Intuitively, just looking at the beam, then assuming everything is uniform, half mass goes here, half mass goes here, and they only act for the linear motion, not the slope, not the rotation. So ignore anything about the rotation. Okay? Because the Gauss equation doesn't say anything about the rotation, everything is going to be linear motion. So those are coming from a little bit artificial from the finite element formulation, those masses. Okay, but as I said, as you can see, as the area goes to 0, they disappear, so eventually it doesn't matter. Got it? Then I told you that if you can make the mass matrix diagonal, then you can have an explicit technique. So this is diagonal, but unfortunately, you have 0 value on the diagonal. So that's not good for embodying the matrix. So we have to revise the matrix a little differently. That is called diagonal mass matrix. Okay, so we are talking about 3 different mass matrices. One is consistent mass matrix, and one is the lumped mass matrix, which is simplest from just common sense. And then this is diagonal mass matrix. So in other words, we are going to make consistent mass matrix to make it diagonalize artificially. We are just make it to happen, okay, without following any kind of principle. Simply, we just make it this one to be diagonal. But always, important thing is going to be conservation of mass, especially linear mass, have to be conserved in the matrix. So the total mass should be equal to the mass of the element. So in that aspect, one of the procedure, of course, this is not the only way, but one of the procedure is shown in here. So what is said that add the diagonal component of the consistent mass matrix, this is a consistent mass matrix, diagonal component associated with only translational degree of freedom. Not every diagonal component, but component associated with translational degree of freedom. So, for example, if you look at this is the consistent mass matrix. The diagonal is going to be this term. And out of those components, translational degree of freedom is going to be this one and that one. Okay, so you add this one and that one. Of course, this one have to be included. This multiplied to every term. So that's, let's say, alpha. Okay, sum of that is equal to alpha. Right? Then next step, arbitrarily, we set all off diagonal term 0. All off diagonal term 0. We just set to 0. Even there are non-zero value, doesn't matter. I just let that 0. So this very, artificial, arbitrary process. So we set to 0. So set to 0, and divide the diagonal component by alpha. So this component by this alpha. Alpha was in here 152 plus 152, which is going to be 312. So 312 over 420 rho AL. Okay. So divide this, of course, include that in here. By that, then you get this one. Okay. And then the last step is multiply them by element total mass. So total mass is going to be rho AM. So element total mass multiplied by that. So what you do is simply you are going to conserve the linear mass in the element. Okay, that's the main thing. And this number, non-linear mass in here, rotational mass, this one really doesn't matter. I mean, it is non-zero, so that's good. But this value is very trivial. Eventually, as L becomes small, then this goes to 0. So the impact is going to be small, but at least it is invertible because it's going to be non-zero, the diagonal mass matrix. So that's the only purpose. So if you compare this one to this mass matrix, this and that is exactly the same, except that this 0 value replaced by this L square over 78, right? But as I said, this L square of 78, if you say, oh, I'm going to say L square about 70 or 65 or whatever, doesn't matter, really doesn't make much difference because contribution of this one is going to be negligible. Okay, but only thing is we are going to find the number a little more consistent manner rather than just simply arbitrarily putting any arbitrary number in the formulation. Any question? So if you do that explicit technique, then mostly that consistent mass matrix is going to be very common. But when you're going to do explicit, then this diagonal mass matrix is going to be the most common. Okay, so that you don't have to invert the mass matrix itself because very straightforward. Any question up to this point?
Said that this type was more often seen in the explicit ones.
This is for explicit. Explicit.
Because of the fact that.
Because you don't have to invert the matrix. All right, then let's look at equation of motion, especially if you have taken vibration class or dynamics class, then this will be useful. Okay, this is something refresher for you. So equation of motion is mass times acceleration plus stiffness times displacement equal F. So mu double dot plus ku equal F. And if you have a damping, especially viscous damping, linear damping, then damping is going to be represented by C matrix times velocity. So mu double dot plus C u dot plus ku equal F. This is going to be the equation of motion in whatever degree of freedom, size of the matrix. I mean, this column vector, equation of motion. And the damping term, you may already know that, but damping term is usually not coming from mathematics because not many cases, virtually almost none, except very simplified case, the damping term itself we cannot really derive from the mathematical equation. So that is more or less empirical expression. Okay, from experiment, from some observation, then they just come up with some kind of damping term. And again, the simplest damping term is going to be like that, this kind of viscous damping. So damping force is proportional to velocity. So if you look at this door doesn't have the damping damper, and some door has the damper, so you cannot, open so quickly. So those kind of dampers like a viscous damper, so that the damping force is proportional to velocity of the opening the door. So anyhow, this is the more general equation, and this is the equation when you neglect the damping. Many times people ignore damping. Of course, sometimes damping is important, but sometimes damping we ignore that. And for mathematical simplicity, what people propose is so-called proportional damping. So proportional damping means that damping parameter, damping matrix C is linear combination of the mass and stiffness matrix. So mass matrix and stiffness matrix and A and B is going to be some constant to be determined. So once you know A and B and then multiply by matrix K and C, then you say this is going to be your damping matrix. So again, this is just mathematical simplification for proportional damping. Then you can simplify your equation in the further mathematical operation. So that's why they institute that one. And also another thing is that there is no simple way to construct this damping matrix. So maybe people propose that let's try to use some kind of combination of the mass and stiffness matrix like that. Okay. But anyhow, our focus right now is eigenvalue problem. So I'm going to demonstrate the eigenvalue problem using finite element solution technique. So for example, going back to this equation of motion, standard equation of motion, ignoring the damping, then we want to find the natural frequency without damping. So how do you find the natural frequency? Then you assume solution has a harmonic motion. So sine or cosine harmonic motion. So your displacement or whatever u is going to be the magnitude times sine omega t. Omega is so-called circular frequency, radian per second. How many radian per second? That's the circular frequency. And cycle, when you say hertz, is related to the circular frequency, but one cycle is going to be 2 pi, right? One cycle is going to be 2 pi. So omega divided by 2 pi give you hertz. So you see hertz in radio station and communication, megahertz, kilohertz, that kind of nature. That's the hertz. How many cycles per second? Okay. And then period is that how long it takes to make a one cycle is going to be 1 over f, and that's use here capital T. That's the period. So frequency period has inverse relationship, and also you need to be a little careful between regular frequency and circular frequency. They are related but not the same. Okay, circular frequency and regular frequency is related by this 2 pi. Okay, but in the calculation, because you put sine omega t, so this is going to be circular frequency. If you're going to put this one as sine instead of omega, 2 pi ft, then that's going to be regular frequency. Okay. But anyhow, let's just do the simple way, omega t. Then what we do is we are going to substitute this one into your equation of motion. So if you do that, it's very simple, right? U, T, and if you take a derivative, dt, then this is constant. It's not a function of time, so that's just remain here. Sine becomes cosine omega t, then omega comes out from chain rule. And then taking a second derivative of u, right? Then again this constant, and cosine become negative sine omega t, and another chain rule give you omega squared, right? So if I substitute this and this into this equation, what you get is going to be this one, right? So this term, and this is that term. Now here, what I can do is I can factor out this one, common factor, right? And then also this is common. So u bar sine omega t is common. So you can take that outside and then put this one inside of parenthesis. And what you get is this expression. Okay, this is that expression. So look at this. This equals 0. So when you have A times B equals 0, that means either A equals 0 or B equals 0. Of course, both of them could be 0, but in general, this is 0 or this is 0. Otherwise, you cannot satisfy the product is 0, right? So look at that. First of all, look at the right side, starting from here, sine omega t. Sine omega t is not going to be 0 for every t, right? Whatever omega value, unless omega is going to be 0, if omega is going to be non-zero, then this is not going to be 0 for every time t. So that's not possible. So that's not the option. And second one, u bar. U bar could be 0, but u bar could be 0 means in here, u bar is 0 means the whole thing, this is going to be 0. So in here, let me write down in here, ut is u bar sine omega t. Now this equals 0, then whole thing equals 0. So that we call so-called trivial solution. So it is a set of solution, but we have no interest because it's going to be just, provide any new information. So nothing happening. Okay, that's the one of the unique nature of the eigenvalue problems. And so you have a trivial solution, which we are not interested in. So again, that's not what we are looking for. Then the other option is going to be this. Something inside the parenthesis should be equal to 0. Right? So if this is going to be 0, then of course this is not 0, but u bar vector this one doesn't have to be 0. However, we don't know the magnitude. In other words, in this solution, this could be any value, right? Undetermined. So then how do you make this one to be 0? This is the nature of eigenvalue, right? And if you have taken some matrix, the math class in matrix or linear algebra, anything, then you learn about eigenvalue. No? So you have a matrix A. I want to find the eigenvalue of the matrix A. How do you find the eigenvalue and eigenvector of matrix A?
Use
Use MATLAB. Okay, that is correct, but that's not the answer I'm looking for, right?
Is it minus gamma I
Minus gamma, lambda, or gamma,
I?
I.
Probably take that and then you find the determinant of that new matrix.
Right? That's the way you find it, eigenvalue. Once you put eigenvalue, find eigenvalue, then you can find eigenvector. So basically U bar is going to be eigenvector and omega square is going to be eigenvalue. Then you're going to see that, well, this and that is different. How come this is eigenvalue problem? So this is standard eigenvalue problem, okay, mathematically. This is called generalized eigenvalue problem. The reason is if you pre-multiply by inverse of the mass matrix, so if you do that, mass matrix inverse and K minus omega square, and inverse and mass is going to be identity matrix, right? By nature. So that is going to be equal to this one. Okay. So this is called standard, this is standard eigenvalue problem, and this is the generalized eigenvalue problem. So to find this one, as you know, stated, determinant of this one have to be 0. Okay, determinant of that have to be 0. Then what do you mean by this determinant of this matrix called 0? When you have a matrix A and determinant of the matrix A equals 0, what does it mean physically?
That it's, that you can inverse it, or that,
You cannot invert it.
Yeah.
Right? Or another way is that the matrix equation, the expression, are not linearly independent. What do you mean by linearly dependent, linearly independent? I'm going to give you just simple graphical illustration. When look at two equation is, a linear equation going to be represented by line. So this one equation, there's another equation, then you have solution, right? They are linearly independent. When you have line like this, parallel line, no solution, right? Then they are linearly dependent. So in other words, you cannot find solution, your matrix is going to be singular. Okay, so here, eigenvalue problem is purposely, we are going to make the matrix to be linearly dependent. All right, if this is linearly independent, then means there's no way you can set this equal to 0. You only get trivial solution. So that's not what we are looking for. So we want to have this equation to be linearly dependent, so that your matrix, like determinant of the K minus omega square M, should be equal to 0. From there, you can find eigenvalue, and then solving that equation, you can find eigenvector. So eigenvalue is in vibration class, that's going to be, in this case, the omega square is going to be square of the natural frequency. Omega is going to be natural frequency. And then, of course, angular frequency. And then this is going to be eigenvector is going to be the mode shape. Okay. So in vibration, you determine natural frequency and mode shape. And then mode shape, we only know that relative motion of the movement, but not firmly determined. In other words, that if I have a beam, okay, the motion of this one, I know motion of that one is going to be, let's say, magnitude is going to be, this is twice of this one, okay? So I know that the relationship, but whether this is going to be 1, 2, or 2, 4, we don't know. It could be anything, okay? In other words, it's not unique, but we know the relative motion of that, the vibration, that's the mode shape. So every system has own natural frequency. Okay, every dynamic system has a natural frequency, and I believe you have your natural frequency too. Have you checked your natural frequency? No. So I'm not suggesting any kind of impact loading or like mechanical way to check the natural frequency. You listen to music. So when you have listen to music, now what rhythm you are going to, your body is going to, move around. So we are looking for the resonance, right? When you excite that the system with different, frequencies. So when the excitation frequency match with the natural frequency of system, then system is going to have resonance. Then they are going to have vibration continuously, then eventually the failure, unless you have some proper damping, right? So in the same manner, you listen to different music, then which music conjoined for dancing or you move your body, that's going to be your natural frequency. Again, you do not control your body, then you're going to be, get tired very quickly, right? So that's the way you can find the natural frequency. So natural frequency is very important to avoid any potential failure. So we don't want to operate the system under, close to natural frequency. All right. So if you see some kind of operation, the manual, then they said that, you increase the motion velocity or something up to some point, and beyond that point, you have to move quickly, because that's going to be the band of the natural frequency, that the range. So by moving quickly, so you don't have enough time to accumulate energy, so that you avoid any potential failure. Okay. All right. So this eigenvalue problem is actually to find such a natural frequency and mode shape. So let's look at some example problem here. Again, for simplicity, we are looking at free beam vibration using single element, just one element. So 2 node and 4 degree of freedom. So you got stiffness matrix, okay? And then just for simplicity, we say everything is 1. So raw air, mass is 1, and beam rigidity 1, length is 1. So just for, to make this simple. So everything is 1, that's going to be your stiffness matrix. Then mass matrix, let's look at 2 different mass matrix. One is going to be diagonal mass matrix, one is consistent mass matrix. We didn't look at the lumped mass matrix because of 0 value, so we cannot invert the matrix sometimes. So then we just look at those 2, and then we look at that. So actually, determinant of the matrix equal to 0, and we found the eigenvalue and eigenvector. And eigenvalue, we have a 2 zero eigenvalue and 2 non-zero eigenvalue. So total 4, because this says 4 degree of freedom, 2 zero, 2 non-zero, and the corresponding eigenvector. Okay, This is that U1, theta 1, U2, theta 2. So what does it mean? This eigenvector is that your U is H1 plus H2 right? So this function of x, this function of x. So plugging this into here, now this will give you a motion. Okay, we are going to talk about it in a minute. So that's what talking about the mode shape. Then first of all, let's check that qualitatively. Okay, qualitatively, whether this makes sense. What does it mean? Are we allowed to have two zero eigenvalue? Zero eigenvalue? Is that acceptable or not? What do you think?
Say no.
No?
Take your time, I have to have a unique solution.
So no means this calculation is incorrect, right? Right? This calculation is incorrect. I'm sure you have not seen zero eigenvalue in most application because that's not the our interest in most cases. But in here, the zero eigenvalue makes sense. Why? What do you mean by zero eigenvalue? When you have rigid body motion, right? When you have a rigid body motion, then you are going to have zero eigenvalue. So rigid body motion does not have any vibration, just moving, Then Y2, not 1 or 3, that Y2 zero eigenvalue.
One for linear movement and the other one looks like it's for.
So what you said is correct, but different direction. So one is going to be linear transverse, right? And the other one is going to be rotational. So you have a two different rigid body motion. Translational rigid body motion and rotational rigid body motion. So you are going to have a two zero eigenvalue. Okay. So number of eigenvalue should be equal to number of independent rigid body motion. You get it? So those two represent rigid body motion. Then the other two now represent actual vibration, non-rigid body motion, vibration, mode shape. Then, okay, how do I make sure that's the rigid body motion or not? Look at, excuse me, this motion. Look at this motion. If you plug this one here with H1, 2, 3, 4 in chapter 8, and you plot it, then I can show in here that that's the 2 point. So here, this is the V1. V1 is negative, so you got negative 0.7375. And this one, you got negative 0.309. So this is translational movement. And this is the slope. This slope said this is 0.426. This is 0.426. And actually, if you make a straight line here, and if you look at this slope, the difference, if we're saying this is going to be 1 in our model, So this difference is exactly 0.426. So if you plug into here, then you're going to see this straight line. Okay, then this is a little bit different from what you talk about. Unfortunately, in the numerical, the program, they could not separate two ridge body mode. Represent in this separate manner. So in other words, this ridge body motion is going to be combination of translation and rotation. Okay, separating those ridge body mode is not easy in numerical sense. So that this represents one of the ridge body mode, and likewise, if you do second one, then this is 0.008, the first node, and this node is going to be negative 0.572. Okay, and then if you look at the slope, this is going to be negative 0.580. Okay, so again, this is another ridge body motion, but combination of linear and rotational ridge body motion. Make sense? So both 2, 0 indicate ridge body motion, but this the mode shape somehow indicating combination of the two rather than two individual separation. Okay, because the 0 value is very almost impossible to separate out this one. Then what about now non-zero? The third one, that's the lowest non-zero eigenvalue. The third one. If you look at that, then again, look at the motion. This is negative 116, and this is also negative 116, right? And if the ridge body motion, then slope is going to be 0, but this non-zero. You got slope positive 0.698, this slope, and this slope has a negative 0.698. So actually same slope but opposite direction. So if you plot this one again based using the shape function, it's going to be like this. So that's the first non-zero mode shape, like a half sine curve. Make sense? So mode shape makes sense. Now, what about second one? I mean, second non-zero one. So here, and this is positive 0.059, and this negative 0.059, and slope is in this case both negative. Okay. However, if this is going to be ridge body motion, then slope have to be negative twice of this one, which is going to be negative 118, but which is very different. So if you plot this one again based on the shape function, it's going to be like this. Okay, so that's going to be second mode shape.
So you were like inferring, since the omega 2 wasn't 0, that it's not gonna be a straight line or anything, so that's what.
If this going to be, I mean, if this happened to be the 0 omega value, then it should be a straight line, because that's going to be ridge body motion, right? But this is non-ridge body motion, so I mean, what you need to do is just plug into this expression.
That's how you get plotted.
Right. That's what you have to do more precisely. But since I don't want to do this calculation explicitly, so I'm just showing the characteristic. So curve is going to be like that. Yes.
Are you able to predict how many nodes that plot's gonna have?
So if you do this one, then you'll know exactly.
So you have to
Yeah,
put it in
yeah,
to
yeah,
find that.
yeah. But now in our case, that from our common sense, that this, the first mode, second mode is gonna be two wave, right? And third mode is gonna be another one, so that we are using that information. Okay, but more precisely, you plug into here, then you'll get this one. So we are not just cooking any story in here, just simply based on shape function. Okay. So two frequency, non-zero frequency, and two mode shape, and two zero frequency with that one. This is for consistent mass matrix, consistent mass matrix. And if you do diagonal mass matrix, okay, same thing. This is going to be diagonal mass matrix. Then you also get two zero eigenvalue, because again, this is going to be two rigid body motion. And same thing, if you plot that one, that also show you the rigid body motion. If you plot that, that's going to be, just do one more time here. Negative 5.8 and positive 0.043, and the straight line is going to be, this is going to be 0.591. So you can see that that is going to be straight line. So same thing in here, you got two rigid body mode and then two non-zero, and that's the mode shape shown here. Okay. Then if you are going to compare this one with the exact solution, the exact solution is this. If you solve that exactly, not using final element, but you know, then 0, 0, and 501 and 3800 like that. So obviously they are not very close to this one. The reason is because we use just simply one element, right? One element is not going to be accurate to represent the mode shape. Okay. And also another thing is that in this eigenvalue problem, if you find the eigenvalue, then depending on number of degree of freedom, if you have a 1,000 degree of freedom, then you are going to have 1,000 eigenvalue. But mostly finding eigenvalue, even numerically, is time consuming, computationally time consuming. So mostly you are not going to find 1,000 eigenvalue, all of that, because we don't need all those information. Most time we are looking for the lowest eigenvalue. Okay, so the lowest natural frequency, so lowest eigenvalue. So we start maybe from 1 to 3, depends on how many you need, up to 10. So we only determine number of eigenvalue. But the good news is that if you have large number of degree of freedom, the accuracy of that eigenvalue and eigenvector is more accurate for lower eigenvalue compared to higher eigenvalue. In other words, that if you have a two eigenvalue and eigenvector, then the first one is supposed to be more accurate than second one compared to exact solution or whatever actual solution. Why that makes sense? Because that higher mode shape is like this. Okay, higher mode shape, you have much more up and down, right? More up and down means mathematically you have to have higher order or polynomial or higher order number of degree of freedom to match that large number up and down. Okay. On the other hand, if the mode shape is simple like that one, then you don't really need so many, the degree of freedom or node number or element number to represent this one properly. Okay. So naturally, the lowest, the mode shape and natural frequency eigenvalue are more accurate than higher one. And that's what we are also looking for too, because that is more interesting to us, that the lowest one, lowest eigenvalue and eigenmode. Okay. Any question up to this point? Okay, then let's take a break and then continue from here. Michael, do you have any question?
No, sir. Thank you.
All right, so then let's take a break.